Okay. Yeah. Thanks for so many coming back. Very nice. All right. So let me remind you of the setting. There we are. So we have a fixed number of variables, a fixed degree. Everything's fixed. So finite dimensional vector space that we are working in. It's this vector space here. Everything's finite. And so and you have a complexity, and we can take. So usually we want to have this one. This is a bit more instructive, right? So it's a bit simpler questions. But this one works in the same way. Right, and, so in this very general, it works for. So the argument works for different complexities. Is no problem. So you can take this one. So the key thing now is this is a theorem, and is that the set here. So we want to understand the set because we want to show for some fixed permanent that it doesn't lie in here, right? So we fix the degree, so we want to show permanent doesn't lie in here. So the theorem is that if you look at these polynomials whose complexity is at most n, and you close it, this is an algebraic variety. And this is very powerful, right? If you, but it also uses some theorems from algebraic geometry that I think are very important to be understood in quite some detail to advance the theory, right? So what we basically just call these theorems as black boxes, right? So this is a problem. This is a problem. I mean, it tells us that there is this nice structure, but then we need more information, right? We want to know what are those separating polynomials. So we have to understand this much, much better. So okay, let me sketch this. Maybe that's certainly don't say proof. This is proof sketch. Okay, and now so we want to have this additional structure on this set. Okay, so first of all, we prove that it's so-called constructible. So what's a constructible set? You have a set that's constructible. So first of all, algebraic varieties are constructible. And now, and this explains the word, is that you have finite unions or finite intersections or complements are also of constructible sets are also constructible. Right? So you can take arbitrary Boolean combinations. So these are all constructible sets are constructible. That's the definition now. And so you define what's a polynomial map. So you have some map that goes from some complex vector space, say, got some dimension kappa, to, say, your dimension eta.
So just algebraic varieties themselves are closed under some things. So what are they not closed under? Are they not closed under complements?
Yeah, they're not. So they are not closed. Algebraic varieties are not closed under complements. So you get Zariski open sets here, and also, but they are. You can take finite unions and finite intersections. But once you take complements, and now you take complements and take, and now it gets. So you basically have a variety. You cut out a different variety. You remove it. And let me actually maybe give you an example. So if you take, this is actually a nice one. So you take the zero set of y squared equal to x cubed plus 2x squared plus x. So this one has the following. If you plot it, it looks a bit like this. It's a zero, so the zero set is this zero set here. Should be symmetric somehow. Yeah, I mean, my drawing skills are significantly limited. Okay, and there's a point here. There's this point. So this is the zero set of this variety. Okay, I understand it's funny. All right, so this is and now you can remove. So this is the variety, and you can get a constructible set, for example, if you remove the point, right? But then it's not an algebraic variety anymore.
What is the point?
That point is a -1, 0 here. I think it's -1, 0. Yeah, I guess so, yes. You can plug, yeah.
If you draw this over the complex numbers, will it still look like this?
I mean, this is the real picture, right? So this is for the real numbers. This is the picture.
Oh.
Real picture over two variables here, x and y. So there's an x-axis and there's a y-axis here.
It's because the polynomial is positive at some points.
I mean, this is just the zero set of this polynomial.
Yeah, by saying why it's discontinuous, it's where it's positive.
Yes.
There's a where the left hand side is or right hand side is positive, is you have a point.
Yeah, here if you look at this and then here you get this. You touch basically you have a zero here, right, from the right hand side. Yeah. Yes.
But we're over the complex.
Over the complex numbers, I mean, over the complex numbers it wouldn't look like this. I mean, there would be, over the complex numbers the picture is different. Yes. Obviously.
Yeah.
Okay. So, but if you so this is if you remove the point, then this is Euclidean closed still over the reals. But it's not Euclidean closed over the complex numbers. Right? You can still approximate that point arbitrarily closely over the complex numbers. I mean, if you look at the zero set here, if you remove a point from a variety over the complex numbers, always, if it's irreducible. Okay. Anyway, that's just a picture of an algebraic variety, and how you get a constructible set. It's just you remove, for example, a point, still a constructible set. Okay. That's just a constructible set. All right, and okay. And so I want to now write the set here as an image of a polynomial map, because then it will have this property that it will be constructible. So what is this? So I have some map here, and it should be a so-called polynomial map. So it's called a polynomial map. If each of these eta target functions is a polynomial in the kappa many variables here. And now we will find that our sets here will have this structure. We will be the image of a polynomial map. So each of the eta target coordinate functions is a polynomial in the kappa input coordinates. So for example, and this is so this is very instructive, so I think. So example of this is how do we get Warring rank 1 polynomials in this very tiny example here. So maybe let's make this our running example here. So we get a, say we are given alpha and beta, and we'll output a coefficient vector that looks like alpha squared to alpha beta beta squared. And this is the coefficient vector of a Warring rank 1 polynomial, right? So this is x squared, xy, y squared. So therefore the image is here, so the image of this map here, of this polynomial map, is now indeed exactly this, the set of Warring rank 1 polynomials. And you can, you can do this in a very general way. So in general, and it's not difficult to do this, it's just a general, you can always say that, so certainly in our setup, that the set where the complexity is at most p, is at most, as the complexity of p is at most n, is always the image of a polynomial map. And so what is that map? It's the map where you put in the coefficients of all the linear forms that you, so for example, if you have an ABP, then on the left-hand side, you have all the coefficients of all the linear forms that you put on all edges. And now you map it to, and this gives you the coefficient vector of the output polynomial. So that's a polynomial map. It's a bit of it's a very complicated polynomial map, right? But it's easy to describe it. So you get this for Warring rank, ABP complexity, everything, right? And now, so the theorem is now that we invoke Chevalley's theorem. And it says that if you have a polynomial map, then the image of construct.
Can you say it again? Why is it a polynomial map?
Oh, yeah. So why is the polynomial map? So which polynomial map do you take? So you take a polynomial map that that has on the left-hand side. So what you input are all the coefficients of all the homogeneous linear forms on all your edges of your ABP, and that's your and you map it to so you map it to the whatever the ABP outputs, but to the coefficients that are outputted, right? So the coefficients of the polynomial that you output. So that's your map. Okay, so
in some sense, what you're using is that the class has a universal circuit.
Yes. Yes. And
the computation of the universal circuit exactly defines this polynomial map.
Yes, that is true. So you always do that actually. So we always do that. So for Waring rank, it's a universal circuit. For ABP, it's a universal circuit. And so the classical setup was determinantal complexity, where you have a universal circuit, and you always do that. And you want to get rid of the of having several different circuits that you have to work with. You just take one of the universal one. Yeah, take one universal one. And that one, yeah. And whatever it computes is now in the image of this polynomial map.
In the branching program, I think of like a fixed branching program.
Yes, everything's fixed. Yes, indeed. So you need to fix your structure of your branching program. Maybe assume that all layers are same size. So then fix number of variables, you fix your degree, you fix your n also. Okay, let's also do that. Fix n. Right? So this is important. We'll also fix n. And now see what is the structure of this set. Yeah. And then now everything's fixed. And you just get all the polynomials that you can construct. In a finite dimensional vector space, it's a subset. And it's the image of that polynomial map. And so the theorem is called Chevalley's theorem. It says that the image of a constructible set under a polynomial map is constructible again. So, but you start out with just you start with the whole C to the kappa. So that's obviously constructible. That's just the whole space. And now you map it through this polynomial map, and you get something that's constructible. So that's the theorem. And yeah, so constructible has a nice property now. So image of a constructible set under a polynomial map is constructible. Okay. All right. So we conclude the set is the set is constructible. And no, I mean not without the closure, but so maybe we do without the closure at this point. But if the complexity is in n, this is constructible now. That's already very nice, because it has additional structure. Let's find more structure of the set. All right, so there's a theorem that tells you that if you have a constructible set, then the Euclidean closure is equal to the Zariski closure of that set, and that finishes the proof. But you see, I mean, that is not very explicit, right? But this is what it does. So if you have some subset, so what is the Zariski closure? So the Zariski closure of a set is just you take your smallest, so you take the smallest algebraic variety that still contains your set. Okay, so if you say closure Zariski is the smallest algebraic variety containing x.
And is this the same as look at all polynomials
Yes.
that are 0 on x and look
Take
at
the
all
vanishing
the
set.
points that are 0 for those polynomials?
Yes, that is the same. That is exactly that. That is exactly that. You look at all the polynomials that vanish on the set and take the common vanishing set. Yes. Okay, so this is the Zariski closure, and so this is in particular is an algebraic variety. Right now, the theorem is that and it works over the complex numbers. That if you have a constructible set, then the closure is equal to the Zariski closure. So the usual Euclidean is the same as the Zariski closure. And we'll have that the usual closure here, Euclidean, is equal to the Zariski closure.
So this presumably relies on complex numbers because over there...
Yes, this is why I chose this example, yes. This is why I chose this example, because here, this doesn't hold over the reals, right? So there's a subtlety going on here. If you remove this, it's still Euclidean closed, but this says that the closures should actually coincide. Right. So, so if you have these two theorems, then it tells you now that this is an algebraic variety. Yeah. So one has to understand this much, much better to actually find out what are the equations. I mean, to even get hints about what these equations should look like. That you want to have to cut this out, right? This will be important, I think.
So how difficult are these theorems?
Okay, so it's two different ones. I mean, I think it's so. Well, I mean, reasonably difficult. But it takes a significant amount of pages, and I'd like to have actually a nice and concise proof that is independent of any yellow books. No, I mean, you can. It's not that you have to go to page 250 or something. That's not that bad, right? It's not that bad. It's reasonable. Okay. It's still reasonable. Okay. Yeah. One has to understand this much better, though. Okay. So, let's just take this now, and I mean, this is amazingly nice now, but we have even more. So we have even more structure on this set. So this is one thing. It's an algebraic variety, but now we also have a group action on this variety, right? So you can actually find more structure. So let me.
Just to
yes.
Confirm. So you're saying that the closure gives you an algebraic variety, but this one was not, right? I mean. This
one was not. No, this one is not an algebraic variety. You can prove that in most cases this is not. So that's very rare that this is an algebraic variety. So for example, if you have Waring rank 1, then this is an algebraic variety. But even, yeah.
So an algebraic variety is closed.
Yes.
So it would only be an algebraic variety if its closure is itself.
Yes. I mean, so there's two closures now, though, right? There's two closures. Yeah.
But if it's a variety, then all the closures.
Yes.
Just preserved.
That's also true. Yeah. Then the closures are the same. Yes. Yeah. So you got to close. Yes, that's true. And this one, yeah. So we've seen examples where this is not, right? So Waring rank 2, border Waring rank 2 was then closed, but Waring rank 2 was not, and so. All right. Yeah. So that is an issue. Yes. So this is also where something happens at the boundary, where things come in that we don't really know how to control yet, right? Well, that's it. Yet. All right.
Do we know to bound something on these polynomials that define the variety? Is there a degree?
I think there are results that make part of these effective, yes. But I don't have the exact bounds for anything. So one would have to look it up. But I do think that there are versions of these things that are certainly more explicit than what I wrote. But yeah, it's just it would take some work to go through that. Yes. All right, let me show you one more thing, though. Okay, so I want to show you one more thing, because that is all very nice, but polynomials is still one can do better, a bit better. So we want to find more structure now on this set here. So we want to study still this set of points where the complexity is the most n. So let's have a look at this set. And now there is, let me do an instructive first example. So say you have a Waring rank 3 polynomial. So you start, say your polynomial is x plus y cube plus. So and I do Waring rank because I think it's easiest to understand what's happening in Waring rank, and because you can easily lift all these ideas to algebraic branching programs. It's very simple, but it's very hard to draw the algebraic branching programs. That's the only reason here. So now you replace now x by say x plus y, and this is a group action here. And so what you get is, the result is then, you do this, you get a x plus 2y Right, so it's very easy. And but what you observe is that the number of cubes didn't change, obviously, right? So under this operation, the complexity is preserved, right? It can actually it could go down under this, but it cannot go up, right? So if you do things like this, and so this means that there's a short notation for this. So this is what people in representation theory use. They use a short notation, which is they put a matrix. And they put the linear forms where you in the columns. So let's say x is replaced by x plus y, and y is preserved by just y, replaced by just y of p. And and this is this polynomial here. Right, this is a way of writing this. So columns are let me actually put this maybe. So variables are replaced by homogeneous linear forms given by the columns. That's the usual way of doing this. Because if you do this, it has a nice property. I'll tell you in a second. So the variables are replaced by homogeneous linear forms given by the columns.
Or you can just think of it as the composition of P with the matrix.
Right.
Yeah. With the linear.
Oh yeah. You can that is true. You can think of it like this. This is very true. All right. So so you observe then, and this is now obvious. If you have your viewpoint, this is now obvious that if you have a G1 and have a G2 and you apply them, then it's the same as G1, G2, and apply it to P. Right? This is now obvious. So and this is what you want. So this is the axiom of an action. Right? So now you have an action of your monoid of matrices. Now they can move your points around, and so the Walling rank also doesn't. So actually, your complexity, you can do this now for Walling rank or for algebraic branching. Problem complexity doesn't really matter, so it cannot go up if you do that.
If you take invariable matrices, it's the same. Right?
Sorry.
Invariable matrices would be the same.
For what? For
invertible?
Yes, for invertible matrices it's the same, yes. Indeed, so for invertible matrices, obviously from this argument, it's the same. So therefore, this means that the set here has a structure, right? So that you can now apply matrices that are invertible. That's exactly what your remark is, right? So this means that you can apply matrices. Sometimes people write it like this arrow here. So you can apply matrices here that are invertible. Say we have m variables, then this is GLM. Now you can apply these and have some additional structure on your set. Yeah, so this is very nice. So we call this this is now called a GLM variety, right? Because it's a variety, it has a GLM action on it. And so if you have that, then you can do you know much more about how to separate points from your variety, because of a conceptual thing that happens now on your functions. So if you want to separate your variety from a point, you do this with a function that vanishes on your variety and it doesn't vanish on your point. So if you study now these functions, then this action lifts to the functions in a canonical way, right? And it's a conceptually very interesting way, but it's completely canonical. So you can maybe let me define, because now this is what we are working in. So define. I want to work in some space of polynomials of degree delta, and the coefficients should be polynomials of degree d. So the variables should be polynomials of degree d in m variables. So let me just write it like this, and maybe say this is the polynomial ring, but the variables are the polynomial. So this is a finite dimensional vector space inside of the xm, where there's a different notation of this. But this is this kind of thing that we are working in, right? So the example would be here the discriminant. There was delta in d and m were all 2, right? So let me do one example here. Or maybe a bit more instructive is if you put the dimension, then you know precisely what this space is. Right? So the dimension is this binomial coefficient, but it's all nested, right? So there's a d plus m minus 1 choose d. plus delta minus 1, and then there's choose delta. And so this is a large dimension. And so, for example, you have that if you do everything is 2. Yeah, so let's have a look at our very simple discriminant example, where the b squared minus 4ac lives.
Sorry, what do these subscripts d and s mean?
There's not an s, this should be a delta.
Oh, okay.
I try to make a delta here. And that's a delta, and that's a degree.
Oh, okay.
The subscript is the homogeneous degree delta part. So yeah, let me give this example here. Okay, so this has a basis, and the basis is given by a squared ab, ac, b squared, bc, and c squared. So here in poly c squared, poly 2c squared, every polynomial, so every this has a basis. You can maybe so maybe you can write ABC here, and now you take polynomials here to homogeneous degree 2 polynomials here on the set. Right. So in particular, you have here you have the discriminant, right? So there's b squared minus 4ac. This function here is living in here, and you can check, for example, if you can evaluate it here at these points to check if it's a So there's 2 levels of polynomials. Right? So this is a bit the problem. So it's nested. Right? That's a conceptual issue, and that everything is polynomial.
So you wrote C2 on one side, but there are 3 variables?
ABC, because those correspond, so this is also already, this is the first thing. So this corresponds to x squared, xy, and this corresponds to y squared. And that's all the 2 variables in degree 2. And they have coefficients ABC, and now you go to degree 2 on that one, and you get this one here. And that's one element of this space. And that's
the kinds of things that you're saying is that if you replace x by x plus y here,
yes,
the a's, b's, and c's.
Yes, exactly. Now, if you replace, the simplest one is if you just switch x and y. Let's just say that. Well, this switches x and y. So in here it would switch a and c, right? So if you do this on the coefficient vector ABC, then you get CBA. Right, but now this also works, of course, if you have polynomials in those variables. And so this is a bit a simplified version of this, but this is how one should look at this. So in particular, if you look at the b squared minus 4ac, well, that's you replace a by c and b is fixed, right? So this is still b squared minus 4ac. And if you're now into tedious calculations, then you can actually have a look at what happens if you take any 2 by 2 matrix and you apply it to b squared minus 4ac, and you'll get that this is the determinant of g squared times b squared minus 4ac. Okay? So the discriminant has an important property. It is invariant under determinant 1 matrices, right? So the special linear group preserves this polynomial. And all right, it's good. So, but this is a bit of tedious calculation. So, okay. So what does it? Okay, so this is very good because now we actually do. Okay, so what we just saw is that actually we do have an action of GLM now on this finite dimensional vector space over here, right? And that's very nice because the representation theory will help us to find out what polynomials could possibly be the ones that separate our point from our variety, because that's what we want. I mean, separating the point from the variety is equivalent to having a lower bound. Right? It's the same thing. All right, so we want to do that. And for that, I want to define the type of polynomials that are now of interest. So there's a very special type of polynomials that we only have to look at, and those are called highest weight vectors. And for defining this, let me first define what is a partition. What combinatorics people call a partition. So you have an M tuple. So I call it lambda. Lambda 1 up to lambda m. So I'm trying to define now a special type of polynomial here, and that the discriminant will be one of those. But yeah, bear with me for a minute. Okay, so this is called a partition. If it's non-decreasing. So you have lambda 1 greater or equal to lambda 2 up to lambda m. Okay. And so now I want to have what is called a highest weight vector. So if a lambda is a partition, then a polynomial, let's say we call it, say the polynomial should be f, and it should be something like the discriminant. It should be in the poly delta, poly d, c to the m, some polynomial that is on the space of polynomials. In this very special case, I want to have a look at this. It's called a highest weight vector of weight lambda where the following holds. So two properties that define this, and one of them is if you apply g to f, then this should just be f as long as g is upper triangular with ones on the main diagonal. Okay. So for example, the discriminant has this property because the determinant of these is just 1. Okay, so that is true. And the second is, so you want, if you have a diagonal matrix, say you have some constants here on your diagonal, alpha 1 up to alpha m, and you apply it to your f, then it just rescales. And how does it rescale? It rescales by alpha 1 to the lambda 1, alpha 2 to the lambda 2, so that just tells you how it rescales. And yeah, and so the discriminant also does that. So the discriminant actually rescales. So if you do this on the discriminant, maybe, yeah, it scales with a 2, 2, right? So if you do that, alpha 1, alpha 2, 0, 0 on a b squared minus 4ac, then this will give you alpha 1 squared, alpha 2 squared times b squared minus 4ac. So this is the highest weight vector of weight 2, 2. Okay, so why did I define this? Okay, so this is the highest weight vector because of the following. Yeah, because of the following theorem now. So, and this is the theorem that says that whenever we want to prove a lower bound, then we might as well just prove a lower bound using highest weight vectors only. We'll also be able to separate. And it's much less than all the polynomials. It's just very few. I mean, significantly less by orders of magnitude. Okay, so the theorem says that so if you have a GLM variety and you have a point that's not in the variety, okay, then you will always find the highest weight vector let's call it f maybe, of some weight lambda, and it will separate. So it will have on your variety it's constantly 0, and on your point you want it to on your point to be non-zero, but that's not quite true. You have to move your point a bit, so you have to disturb perturb your point a bit by some g, and g is some matrix. So this is non-zero for almost all g and GLM. So that theorem tells you if there's a lower bound, then highest weight vectors will prove that lower bound. Right? So one has to understand the highest weight vectors. Right? There's much less vectors than polynomials in total. So in particular here, so there's this one highest weight vector, b squared minus 4ac, and there's a second one, which is, so I mean up to scale, of course. So I mean every scalar multiple is also highest weight vector. So this is highest weight vector, so b squared minus 4ac is the highest weight vector of weight 2, 2. And there's another highest weight vector, which is just a squared. And those are the only two in this vector space. But the vector space is 6-dimensional, right? And here the weight is 4, 0. Well, those are the two vectors that you get. All right? Let me maybe show how this works.
So, I mean, it's good on one hand, but on the other hand, you have to deal with this almost all GLM.
But that's only, I mean, that's not so crucial, because the only thing that you need to do for the lower bound is you have your point. So, I mean, you want to prove that some polynomial doesn't evaluate to 0, and you only have to pick some g. You don't have to actually do this for almost all g, right? You just have to, and if there's a lower bound, then you find something that vanishes.
You have to exhibit the g. Yeah,
yes, you have to exhibit some g. That is true. That is true. But usually, I mean, yeah, but you don't have to exhibit some g's that something vanishes. You only have to exhibit some g that this is non-zero, and this will be true for almost all of them. But I agree. Yes, I agree. No, I agree.
I mean, I don't have a sense. I'm just saying.
No, it's just so that wasn't. So this hasn't been the issue so far. I'm just saying.
So typically, just G being the identity or something works.
Yeah, that depends on your setup. Usually, some a bit more complicated matrix works though. It should be a bit more complicated. Yeah. So usually you take some. You take a tiny bit of different matrix. So, because if you have a lot of zeros in the matrix, then the evaluation is likely to be 0, depending on your way of constructing the highest weight vector. So you put some entries.
This is true of every algebraically closed field?
Characteristic 0.
Characteristic 0. So the representation theory works over characteristic 0 all in the same way, yes. You will always have, if your characteristic is 0, you have, this is just a, I mean, you will see from the proof, it's a very simple fact from, you just need your group to be reductive. And you need your general linear group to have, the irreducibles should have the single highest weight vector. And you have that over rational numbers, for example, also. Yeah, okay, let me show you. So I think this is a good thing to just show you. So we started at 11, is that true? Okay. Maybe, let me sketch this. All right, so it uses some representation theory, right? So what you do is, so this is called a representation now. So you have a group action here on a finite dimensional vector space called a representation. And so you use the fact that this decomposes into what is called irreducible representations. And what's an irreducible representation? It's just so you can decompose this vector space here into direct sum of smaller vector spaces. So you take a vector space and you decompose it into some small vector spaces, and they should be all closed under the action of GLM. Okay, that's what you want. Yes.
Separating polynomials that we get from, say, partial derivative based lower bounds or shifted partial based lower bounds,
yes.
Do they have this property?
No, they don't. They are usually a linear combination of points that are not. So they are not highest weight vectors, but they are linear combinations of applications of matrices to highest weight vectors, and you get linear combinations. It's not so easy actually to find out what.
Are there examples where of lower bounds where sort of the natural separating polynomial is a highest weight vector?
Yes, so Strassen, for example, proved a bound on tensor rank where this works. And then we have some works on this also, where we prove also tensor rank lower bounds using these techniques. Also, there's Landsberg's result on Landsberg-Manivelle-Resser also gives precisely the type of the highest weight vector for the determinantal complexity of the permanent. So that's also happening. Yes.
And the sort of the highest weight vector analogs of lower bounds via partial derivatives or shifted partials. So you're saying if there is a separating polynomial, then there is one which is the highest weight vector. So
yes. So you have to decompose. I mean, so basically for shifted partials, you get this huge matrix, and you take a minor of that matrix, and that usually doesn't have these properties, but you can get it decomposes. So one of the summands actually would have the properties of it.
These summands, they have some natural sort of interpretation.
Of that matrix, I'm not so sure if they have a natural interpretation in terms of that matrix. One would have to have a look. That would be very interesting. So I think usually if you want to, I mean, okay. So this is a if you have some lower bounds method, and this tells you that there is also a highest weight vector, then usually it's not clear if it's easy to find what kind of highest weight vector that is. So, right? I mean, you have some lower bounds method. How would you know, right? And then there are methods of trying to find this out. So Landsberg, for example, in the papers does these things, find out precisely. Because it's not just about highest, I mean, this is about highest weight vectors, but it's actually the type of the irreducible representation that separates, right? It's about this lambda here. What is the separating lambda?
So you have one highest weight vector per partition?
In here, you have actually more than that. So in here, so you have the following. Okay, so I'll tell you. So those are irreducible. So this means that there's no subspace anymore, right? That is also, so there's no fixed subspace anymore. So your group acts in a way that you cannot decompose further. But now each one has a type. So each VI, so the VI are irreducible, just means that you cannot decompose them further into this direct sum here. And each one has exactly one highest weight vector. Of some type lambda, but you might have several ones. Okay? So, and now, okay, so that is, but that basically proves, this basically proves the fact. Because now, so, okay, so this basically proves the fact. Because what you look at is, you look at the functions that vanish on your variety. Say, we call this Ix delta. Should be inside it's the vanishing idea, right? So the functions that vanish on your variety. So this should be the functions that vanish, okay? So now you also have here on this one, so let me maybe define this properly here. F that such that f of x is actually vanishing here, right? So it's the set. So now here you also have the group actions. There's actually a sub-representation of this one here. So here you have the same group action. So therefore this one also decomposes in the same way. Also in a different, in the same kind of manner, but as a sub-representation, so you have less summands. Right, and then each of the summands has one highest weight vector. And now, so you decompose. This gives you some decomposition here. Those are irreducibles. So Vj are irreducible. And now, each of the, so each Vi or Vj here has exactly one highest weight vector. And moreover, each of these Vj is equal to the span, this is, okay, of that highest weight vector. So for each Vj, you get a highest weight vector Fj. And so Fj is the highest weight vector up to scale. I mean, but scale doesn't matter because you can rescale here. Okay? So this means now that if you have some function that vanishes, or some function here, you decompose it, not just over this decomposition, but even further here over this decomposition. So you get a basis here that is just given by some GIFJ. So here, for example, you get this means that you get, each Vj has a basis given by some GI times Fj, right? Because it's a linear span of just applications of here. So okay, so now you get that your vanishing polynomial, it's in this space. But you have basis vectors that are all of this form, right? Now, okay. So now your function doesn't vanish on the point P, so one of those doesn't vanish on the point P, and that's it. But this one was taken from here, right? So the only thing that you did here was you decomposed the whole vanishing idea into functions of this form that are all of the form GIFJ. So therefore you find, when you do this, you find there exists I and j such that GIFJ, if you evaluate at P, is non-zero, and also GIFJ is actually in the vanishing ideal. And this proves it because this here, this is the same as Fj applied to, this is the way that we defined this, Fj applied to, so you put a transpose here for technical reasons. But this is just, this is the same. So when we defined this action here, I didn't say this, but when we defined this, you basically defined the action on your polynomials via the action on your polynomials that you work on, the coefficients. Right? So this is the same. I mean, if you have an action on your polynomial here, on your testing polynomial f, on your f polynomials, then that's the same as basically just applying this to p instead. Right? That's the same. That is how you define this action. Okay. And in this way, I mean, so in this way, this proves the fact, right? You decomposed now the evaluation of your f at p into a sum of these kind of evaluations. One of them must be non-zero because your original polynomial was not zero at your point. Yes?
Can you please explain why does each one has exactly one highest weight vector?
Okay. So that's a complete classification of the irreducibles of the general linear group. And you can look at the weights that so a weight is you apply a diagonal matrix to your vector and you see how the scaling happens. And then for each irreducible, it's completely known how what are all the weights that appear, and they form a there's a partial order on the weights, and they form a partial ordered set, and there's a one maximal point, which is called the highest weight. But that requires basically the complete classification of the irreducibles of the general linear group.
So it's not abstract. It's not an abstract statement for every algebraic group.
You can. You can. You can do this more generally than just general linear group. Yes. That's much more general. Yes. There's a weight lattice in general for the Lie groups. You can do this in a very high generality if you want to. Yes.
So when you say it's exactly one highest weight vector, are we saying one f or one vector lambda?
So one f, and that f has also one lambda, and but the lambdas might repeat. So let me define actually what is the multiplicity. There can be several lambdas actually of this, several f's of the same type lambda, and that is a thing that the original GCT conjectures were concerned with. Right. So you want, I mean, this might be complicated to look at these highest weight vectors. I mean, it's a nice theorem, but then now, it's true and a nice theorem, so you can separate with those. But it might be difficult to do that. So what you want to do is you only want to look at how often here does my type lambda appear. Actually, each of these VJs has now a lambda attached to it. And so this decomposition is not unique, but it turns out that the number of times that each lambda appears, that's actually well defined. So you can decompose in several ways. What the types and how often they appear, that will actually be the same. That's all non-trivial bit. But it's not so very hard. It's also in the lecture notes also, so you can look it up. And but let me define. So because this will maybe be enlightening. So if you define the multiplicity in any representation, so you have some representation, say V with a squiggle thing, and you define as the dimension of the space of highest weight vectors of type lambda in there, right? So if this is irreducible, there's one highest weight vector, but it could be some decomposition like this, right? And then you would actually get several highest weight vectors of the same type lambda, and they span a vector space. They span actually a linear subspace, right? And that's called the multiplicity. And the multiplicity is also the same as the number of times that your Vj actually has type lambda in this decomposition. Okay, so that gives you what is called the multiplicity. So let me give you examples of multiplicity. For example, the multiplicity of 2 in poly square C square there's 1. This is because there's the discriminant, right? And then we've seen the other one for 0 is also 1. So you get these natural numbers now. You just get a bunch of natural numbers. But if you get any other, say 3, 1, then this is 0. And so one can calculate these numbers. And yeah, and now try to use that. So that's actually an open problem. So open problem is a big open problem. This is Stanley's problem number 9. So Stanley, so this is Richard Stanley. Number 9. From a list that he compiled in 2000. And he wants to know this number here. What is a count? That is what he wants to know. So in other words, so the map. If you have a map that's you're given some lambda, some delta, some d, and some m, and you map it to this multiplicity here. Is this map in sharp P? That's the question. That's not how he phrases it, but that's the question. So is this map, is this in sharp P? So what does it count? And we know that it's in gap P, but that's not enough for combinatorics people. Right. And now you can use actually these multiplicities now for lower bounds. That's the last thing I'm gonna say. So you can use highest weight vectors. So people then thought, I mean, what about just looking at how many highest weight vectors of a certain type are there? So, and that is, you want to prove that a point doesn't lie in your variety. Well, your point lies in your variety if and only if its whole orbit closure is a subvariety. Right? That's true, because yeah, that's the smallest set that's closed under the group operation and also Zariski closed. And say you call this y. Okay? And now, this is now a question, so your lower bound question here is now a question about inclusion of two varieties into each other. Right? And they both have some structure like this in their vanishing idea. Right? So they both have vanishing ideas. So in particular, so if y is a subset of x, then all highest weight vectors so then all the highest weight vectors that vanish on x, they vanish on y, right? Y is a subset. So this means, so if y is you want to disprove this fact, right? You want to disprove. So what you get is that the multiplicity in the vanishing ideal of y, delta, is actually greater or equal to the multiplicity in the vanishing ideal of x, right? So this is what you would get. And now, and you call this, and so if this is violated, then you call this a multiplicity obstruction. Multiplicity obstruction. So usually this is phrased in a, usually you do this dually. So you, in the dual way, so you do this over the coordinate rings. So instead of the vanishing ideal, you look at the coordinate ring. So you say, I define this as the quotient. So I say, this is just poly delta. So it's just a difference of, so you quotient out the vanishing idea. This is usually what algebraic geometrists do. So therefore you might as well just also do that. And now as a representation, as representations you get that this is just a sum. So you get your poly delta poly d, sorry, this is a d. Poly d c to the m is a sum. So one is the coordinate ring and one is the vanishing idea, right, as a representation. And yeah, so therefore now you can also just look at the multiplicities here, right? Because you know them here, you know them maybe here, then you know them here because they add up, right? That just adds up. So so therefore a multiplicity obstruction is usually written in this way. So it's usually written in this way. It's it is so the multiplicity of in the coordinate ring for x. If that one is less than the multiplicity in the coordinate ring for y, right? So if this is true, then we have a lower bound. So y does not lie in x. And so if this is even 0 here, then this is called an occurrence obstruction.
What's the obstruction, delta or lambda?
So delta is the degree in which it occurs, and lambda is the type of the obstruction. So lambda would be the obstruction. You would call lambda the obstruction. Did I?
Or delta.
That's fine.
I mean delta. There is some delta, but so the obstruction. Then delta is called an obstruction. This is wrong. So there's lambda. Lambda is called the obstruction. So actually the whole tuple. I mean you can take the whole tuple as being the obstruction, right? Or usually you take lambda because lambda actually tells you basically all the other data will be encoded in lambda anyway. I didn't actually say that, but lambda will actually tell you the obstruction, right? So there's some multiplicity that happens to be here. Say maybe with 0 and doesn't happen to be here. And now, yeah, so the question is now, so yeah, obviously several questions arise now. So do these things exist? I mean, is this sharp enough, right? Right, so that's basically the question, because you are restricting now to just counting how many of these types are there. And it's not clear how sharp this is. And so if you have a different model of computation where you don't use the homogeneous model of computation, so if you have an affine model of computation, then you cannot use occurrence obstructions for the lower bound. So that is what we proved. That is based on some work by Kadish and Landsberg, where they study precisely what happens in these affine models of computations and what happens to the representations. And based on that, we can prove that there are no good occurrence obstructions. Okay, but on the homogeneous models, we do not know this, right? So it was the model is much more clean, and we cannot find a way of disproving that these things exist. Okay, and multiplicities. So if you want to just compare the multiplicities, it's open. There's no-go result on this, and so it's possible to prove some things with these obstructions. So as I mentioned, so you can prove a lower bound on the border rank of matrix multiplication using occurrence obstructions, for example. You prove a not very strong, but a non-trivial lower bound on the border rank of matrix multiplication. All the lower bounds that are all the separations that you can do are usually occurrence obstructions. So we recently found an example where you can prove that the multiplicities are actually strictly stronger for separating than the occurrences, just the occurrences. So we do study we cook up some example where this is possible to show that those are more powerful. All right, and and it's unclear. Yeah, it's unclear how powerful this is. So what it does though is in some way, and I'm very vague now. So we studied what is how powerful is it to so what kind of proof? So how powerful is this type of proof if you write down these inequalities? And in some very tiny toy setting, one can say that this encodes a very hard function, right? So it might be very, very difficult for a point. It might be very difficult to actually get this multiplicity down, right? So to actually get your multiplicity might be very hard, and it might be that hard. So it might even be that hard that it breaks an algebraic version of a natural proofs barrier. Right, so it might be that hard. So, but in a very tiny toy setting, we are just first studying this, and yeah. So this is also so we're trying to understand better what's the separational power of these multiplicities, and is it reasonable to conjecture that it surpasses any natural proof barrier if there is any algebraic? I mean, there are papers on algebraic versions on this, right? And it's not so clear how. Yeah, it's not so clear how. So there's no algebraic cryptography. That's basically the issue. So it's not so believable. It's not so clear how believable is the algebraic natural proofs barrier in that sense. So we are just, but that's very, very recent. So we are just studying this. Yeah.
There's algebraic natural proofs, but it's not clear there's a barrier.
That's true. One can, yes, there's algebraic natural proofs, but not clear that there's a barrier, I see. So one, yeah, okay. And anyway, so one can encode pretty complicated, so we encoded the permanent in these things, and yeah, so, but yeah, it's still active area of study. We try to understand, so what is the difference between occurrences and multiplicities? Maybe sometimes occurrences are good enough. Maybe it just was just that this non-homogeneous version was just a problem, maybe. But at this moment it's a bit unclear, right? So the highest rate vectors always work. If you just count their dimension, that's not so clear if it's a valid approach or not. So okay, but I mean, I guess that's good for a bootcamp, I guess.
Questions? So, here you fix the n, the d, and the m, and then we said, okay, look, this is, then we have maybe one polynomial.
Yes.
Separate one from the other, but in the limit, we'll actually have to consider an entire sequence of n's.
Yes.
For one for every degree.
Yeah, you get a lambda for every one. I mean, to get a different lambda for every one.
So, not only does this sort of, we will have to rely on some closed form understanding of the entire sequence of obstructions,
yes.
Right?
Yes. You have an infinite sequence of obstructions in that case. Yes, you need to have an infinite sequence of obstructions. And you have to have some understanding of how these lambdas evolve or if n grows. Yes, that is true. So this happens, for example, for the, if you look at the lower bound for the tensor rank of matrix multiplication, you get a sequence of lambdas, and for each one you get a different lambda. It's getting larger and larger.
So, building on that question, there's a way to index representation of GLN plus 1. So there's a way to look at the, GLN and GLN plus 1. There's a way to compare them, which is just add a box on the first row.
Yes, you can. Oh, the GLM, so that's the symmetric group though. I mean, the number of boxes here, so the number of boxes in your Young diagram is, yes. But there is a way, I mean, you can just increase the number. So M you can increase. And there are inheritance theorems that tell you that basically so the spaces grow a lot, but the representation theory basically stays the same.
So can we somehow say that the occurrences will eventually stabilize?
Yeah, I mean, if you just increase the number of variables, then everything stabilizes quite quickly. But that's not what you also increase D here. And then there are stabilization theorems. But those are usually not the interesting lambdas that you want to look at. You want to have some sequences where you're not actually in the stabilizing range. So we have some example in the first disproof of the first version of the conjecture separating of occurrence obstructions. We actually have, when you find something that is actually in some stable range, then you get actually infinitely good obstructions. So then you can't get, I mean, so everything has some finite complexity, right? You don't want to be in some stable range, right? So you have to somehow get an interesting sequence. Yes?
Is there any connection between these different measures of complexity that you presented? So you had the Waring rank and the algebraic branching complexity?
Yes, so the Waring rank is less than that.
Right.
Yes.
But is there anything else that you can say besides that? I mean, you can separate them.
Yeah,
right.
You can.
Sure, I guess. And maybe you can talk about the width of an algebraic branching program or something like this.
Oh yeah, so yeah, you can. So the different algebraic branching programs, there's classical algebraic complexity theory studies a lot of different types of algebraic branching programs, and if you fix the width, then this is gives you algebraic formulas, and if you let the width also grow with the other parameters, this gives you skew circuits. Yeah. Is that? And there's no way of getting complete VP. So we don't know of a way of getting VP, for example.